we've looked in section 2.3 a little bit more with convergent sequences, things converging to some other limit besides 0. I mean, for that matter, I guess it could be 0. The definition would work for things besides 0 works for 0 as well. And ways we could kind of decompose a sequence, a complicated sequence, into simpler ones that we can identify where they go. Any kind of questions yet? I do have the next homework set, so I should copy it off for you here. So, I think having you do Wednesday the 11th will work. That's, well, how many other things you have Wednesday the 11th? Right before fall, right, everything's due.
We're like, I bet it's going to be doing that Wednesday. They're like, yeah. Okay, we'll get it done.
Yeah.
I'm running out of space on that day.
Yeah, this one, 5 of 7 problems. Actually, there's another page to this, I think.
No, there's
I
not.
think we're good, really.
There's only 7 problems.
Well, okay. Well, the other groups, you can add as many as you like.
Yeah, you can have as many as.
Well, there were going to be 2 more that were multiple choice that I was going to give. But otherwise, it's only out of 85.
Yeah. Wait, there's multiple choice?
I have 2 multiple choice questions. There was a second page. When I ran to make a copy, I forgot there was actually a second page to this assignment. You don't have the second page.
So we still have to do 5 of 7 plus the.
Plus these 2 that I'll
There's multiple choice.
yeah.
At least.
I guess 20% because there are 5 choices, but no.
Really encouraging.
So the multiple choice ones are things we've not talked about yet, so I'll work on that to have for Friday. Although actually, I'll print my another copy and bring it to everybody else on Friday. Somebody on a bus Friday. Leaving on a bus.
Yeah.
At what, 11?
Something like that,
Yeah,
yeah.
sometime before 2 o'clock.
Yeah.
So, oh, but also, before I forget, I don't want to take class time, but I think you 3 signed up on the tutor list. I got an inquiry about tutoring. I'd like to kind of talk to you after class.
Boss. You'll have to find it out.
Well, you can already count me out because I've already got something I'm tutoring and I don't have any. So you can count me out too. I'm tutoring someone.
Okay.
All right, Jay.
Depending on what it is, I might be able to.
Well, I have others too. So I guess you can stay and we can discuss this, or I can keep looking for this person. So, all right. So we want to look a little bit more at convergent sequences, then we want to kind of turn the corner and what if a sequence doesn't converge? We've done some talking about that if the limit's not L, how would we know that? But not so much of how do we know it doesn't have a limit at all? What kind of things would happen if it, or what would we have to say to show it doesn't have a limit at all? But before that, a theorem that they give, if the limit of a sub n is L, then there is a capital X such that a sub n is greater than 1/2 L for n greater than capital X. So what we're saying here is we've got some sequence, and we have decided already that yes, it is converging to a limit L. So we do know the terms are eventually close to L. Somewhere out here they do get really, really, really close to L. and so there's a spot where they're really close to L, but this is saying not that there's a spot where we're really close to L, but at least we're more than half the limit. So that we reach a spot where everything is up here. Now, as my picture kind of indicates, hopefully when we see that we think, well, that kind of makes sense. I mean, if eventually all the terms are getting close to L, we should be past 1/2 L at some point. But what would a proof of this theorem look like? I mean, how would we argue more than just, it looks like that ought to be the case? What would be our standard of proof in a case like this? Well, let me see if I can write this out more than kind of our proof, our argument about this. So, this would be one we don't, I wouldn't say we don't need a preliminary analysis. I'm not sure preliminary analysis is going to be helpful or something we can do, because in fact here we know we have a sequence that's going to a limit. That's the assumption. We're told there's a sequence that is approaching a limit, and we're trying to use that information to prove something else. So if we think, what do we know? Well, the sequence is approaching a limit, which means for every epsilon there is an x. That's good, I'm supposed to find an x, where something happens. Well, in this case, the what I want to happen is different than what convergence guarantees, at least on first appearances. Convergence guarantees an x where n greater than x implies a sub n minus the limit is less than epsilon. So convergence guarantees we get close to L. How can we use the fact that we're close to L to help us argue that we in fact have to exceed 1/2 the limit? Because we don't know what the limit is. We don't know what the terms look like. So we really can't come up with a formula for capital X, because we don't have any other formulas. And yet we're still trying to come up with some sort of argument that here's a way we can produce an X, and here's how we know that it actually works. So that part is kind of the same as proving the limit. We're trying to produce an X, and then show that it really works. So we're going to look at this. Anybody have any kind of ideas on what we might be able to try to kind of merge the language that we know, or we're assuming that is true because we've got the sequence converges, to the language of what we're trying to show? Because there's a lot of similarity. We know there's an X past which something is true. We want to show there's an X past which something is true. So the difference in these two statements is, what are we interested in showing is true? What do we know is true? What are we trying to show is true? Everything else is similar, right? There's a capital X produced past which we're looking at something. So can we think of anything that might help us make the connection here between what we know, that we've got this sequence that is converging to L, and what we're being asked to show? Add maybe a little bit more to the picture and see if that might help. So what we know here is, for an epsilon, for some epsilon, we could go up an epsilon or down an epsilon, there is a capital X, past which all terms are in this band. A sub n minus L is less than epsilon. We go no farther than epsilon above or below. Now, the way I drew it, I guess that there's no real guarantee that L minus epsilon is actually bigger than 1/2 L. It might be below. So it's not, I would say, obvious how these two are related. Could we make it obvious how they're related? In this game, we can pick an epsilon. Could we pick an epsilon where those two are related very nicely?
Which two?
The L minus epsilon and the 1/2 the limit. What happens here if epsilon is 1/2 the limit? And actually, I think probably here, the assumption is the limit's positive. We could do it if the limit's negative. Well, actually, we couldn't do this if the limit's negative. We could do something corresponding. But if the limit's positive, eventually all the terms have got to be away from 0, because they're all getting close to a sub n. Or, excuse me, they're all getting close to L. But if we let epsilon be 1/2 L, if epsilon is 1/2 L, aren't these two lines the same? L minus epsilon, L minus 1/2 L, is 1/2 L. And so, given epsilon equals 1/2 L, the convergence of a sub n to L guarantees a capital X such that n greater than capital X implies a sub n minus L less than epsilon. And the convergence of a sub n to L guarantees that for any epsilon. The reason I chose that particular epsilon here is that particular epsilon is going to help me move from this convergence to L to what I'm actually more interested in here, in the proof, that a sub n is in fact bigger than 1/2 the limit. So if we work with the absolute value of a sub n minus L less than epsilon, we would have minus epsilon is less than a sub n minus L is less than epsilon. Or L minus epsilon is less than a sub n is less than L plus epsilon. And what was epsilon again? Epsilon was 1/2 the limit. We're free to pick it to be anything. And so the limit minus 1/2 the limit is less than a sub n. Or 1/2 the limit is less than a sub n, which was our target here. We were trying to prove that, in fact, the terms eventually are at least beyond halfway to the limit. And in a sense, there's nothing especially magical about getting halfway to the limit. We could get 2/3 of the way to the limit or 3/4 of the way to the limit. Half the way to the limit is probably the simplest distance to go. Half the distance. Which also then would mean if our terms really are converging to a positive limit, eventually they all have to be positive. Now, if we were headed to 1/10, eventually they've all got to be at least bigger than 1/20th. And we can get it, some other number between 0 and 1/10 as well, because kind of once we decide that lower bound, that would define for us an epsilon. And since we know we are given convergence, we're assuming convergence in this case for our sequence. Once we know the epsilon, there is guaranteed a capital X that works. But this is different than a lot of the other ones we've done, because normally we've had a nice formula for the terms. We've gotten a nice formula for X, and it looks a lot more algebraic to work through the proof. This does not look algebraic because there's still lots of stuff we just don't know. So we have to keep track of, okay, well, what do we know? Or what are we being told to? We can't assume here. We're being told we have a sequence that is converging to L. Well, that does tell us some things. That once there's an epsilon, there is an X. And we just have to figure out, okay, what's a helpful choice of epsilon to move us from this that we know to this statement that we're trying to prove? Okay. Another result they give. We've got two sequences. A sub n is going to L, and B sub n is going to M. If A sub n is less than or equal to B sub n, do we think there's a relationship between the limits? And if so, what relationship do we think there should be? Less than, or equal to. I mean, we could have equal to. Yeah, there's no way if all the A sub n terms are smaller, or no more than B sub n, that A sub n could be going something above where B sub n went. In sort of a picture we'd have, say, B sub m, or B sub n, is headed somewhere. The A sub n's are smaller. There's no way it could somehow go to a limit that's higher than m. It might be the same, it might be smaller, but there is no way it could exceed this limit. So we don't know exactly where L is, but we do know it's going to have to be somewhere below the limit for the B. And that can be helpful if we decide if we can decide two sequences are converging and they're related this way, we can do some comparisons. Now, a struggle that we have with our definition so far is if we're going to say a sequence converges, we actually have a pretty good idea of where it converges to. That's part of deciding it converges, is it converging to something specific. So this particular theorem seems a little odd. If we know specifically where the two sequences converge, why do we have to worry about how the terms are related? Can't we just compare the two limits? But we're going to begin to develop some ideas to handle sequences when they're a bit more abstract, of making determinations of, can we decide it converges to something? And if we decide it does converge to something, can we use that information to help us figure out maybe what it's converging to? Or is what we're going to look at today in section 2.4, if we decide it's not converging to anything, what are we going to need to do to back that up? I mean, is it just because we're not clever enough to figure out the limit? I mean, that's a different statement than we're convinced there is no limit. So, if the limit does not exist, the sequence we call diverges. So if it doesn't converge, it diverges, but we very much have kind of a challenge to figure out, how do we know that? How do we know there's not a limit? Because I mean, we could try one limit and convince ourselves, oh, that limit's not going to work. Maybe we could try another limit. Oh, that limit's not going to work. But depending on the sequence, there are times it can be extremely complicated to figure out an argument that no matter what limit we pick, it's never going to work. So, can anybody think of an example they think might be divergent, a sequence that's not converging to anything? Or even think of what a picture of such a sequence might look like. If you're not sure what the terms are, can you think of kind of a picture of what?
Something like x n plus 1 equals x of n squared.
So you want to start maybe with, like, I don't know, 1?
Sure.
Then, well, no, 1's not a good thing to start with.
That's true.
Because then we'd have 1 squared is 1, 1 squared is 1. That one would converge. And actually, if we started with, say, 0.9, 0.9 squared is 0.81, that squared would be smaller, it'd be smaller. So I think we need to start with something bigger. So like, if we started with 2, then we've got 4, 16, 16 squared,
250.
yeah, 256, 256 squared, whatever that is. So as we had to look at the pattern, can we even figure out maybe a verbal description of why we think this sequence isn't converging to a particular number? Are there some other words we might use to describe what is going on?
We're looking for the sequence goes to infinity.
That would be, yes. I mean, that idea going to infinity, or it's unbounded, the terms get bigger and bigger and bigger. So they can't be getting close to a specific number because they keep getting bigger and bigger and bigger without bound. And that, in fact, is what happens with this. This one, it would be called an unbounded sequence. And there are times we would say the limit of a sub n equals infinity, but in terms of existing as a number, the answer is it doesn't. But there is an unbounded, and we would say if the sequence is unbounded, then it diverges because we can't be getting close to a specific value.
So for him to come up with that, did you have to have this equals that? Or could you have just had, I guess I'm confused
Why he came up with that particular, do you have one you'd like to try?
No, but okay, so if you said it goes to infinity, like if you graph x squared, it's going to keep going on forever. So like why, I guess because you're doing like a sequence, or I guess I'm confused why he how you
X of
came
n
up with
plus
that.
1.
Yeah, why he wrote it that way?
Yeah, like,
I mean, instead of, say, x of n is just n squared?
yeah, so like, why did you write it like that though?
Well, actually, these are two different sequences. This one's 1 squared, 2 squared, 3 squared, 4 squared, which also goes off to infinity.
Okay.
So 1, 4, 9, 16, 25. That one also goes off to infinity. And it's actually, I think, easier to convince ourselves that this one goes off to infinity perhaps than that one. And in fact, that's something we're going to be working with. The recursively defined sequences, where we define the next term in terms of the previous one, is always going to be a lot more of a challenge for us to deal with than what I guess I would call a formula for the sequence. Because with the formula, we can do some algebra on that and try to get some idea about what n looks like in terms of epsilon. I mean, we have not really considered any recursive sequence to try to prove that it converges. Because that's just too hard of a problem to prove that it converges and figure out what the limit is. There are some like this where we could probably convince ourselves, oh, it's headed off to infinity, but in general, recursive sequences are much harder to deal with. So if we could, it would be nice to have a nice, more explicit formula for each term of the sequence, because then we can do a lot more algebra with it. So kind of thinking about that, let me pose another sequence to you. And let's see if we think it converges or not, and kind of what the problem is. So I'm going to put this one in recursive form as well. And then maybe ask you, is there another way we could write this? Because I'm not sure. I mean, I guess on yours there probably is another way we could write it, but I'm not sure I'm going to try to figure it out. Oh, I guess we've got 2 squared, 2 to the 4th, 2 to the 8th, 2 to the 16th. I guess we are doubling the exponent each time. So there is a way we could do that. And I guess by mathematical induction we could prove that really is the formula, the way we've done it. But here, if I start with 1, what's the next term?
-1.
-1, and then
+1.
+1, and then -1, +1, -1. Okay. Are we getting close to one specific number? No. There's this sense we're in fact getting close to two numbers, or some terms are getting close to 1, some terms are getting close to -1. We're not getting close to one specific number. I mean, 1 doesn't work. 1 doesn't work as a limit here because for epsilon, say, 1/2, or for that matter, epsilon 1, no matter how far we go out, we're still going to have these pesky terms that are down here at -1. Going farther out isn't going to fix the inherent problem here that these terms are not all getting close to 1. Similarly, if we argue, well, -1 ought to work, well, then there are pesky terms up here close to +1. No other answer is going to work. I mean, we couldn't even say, oh, how about 0? Because for 0, if we go with an epsilon that's fairly small, none of the terms are between -epsilon and epsilon, no matter how far out we go. None of them get in there. They're always staying away from 0. But there is a situation we can argue, I think, reasonably effectively that no limit is going to work for us here. Can't be 1, can't be -1, can't be 0, can't be anything else, because there will always be a value of epsilon where there's no capital X that's going to work for us. We can't go out far enough in the sequence to make sure all the terms stay within epsilon of our limit. And the reason we can't do it is there is no limit. This sequence is diverging. Can we think of an explicit formula for x sub n here? We defined it recursively. The next term, -1 times the previous term. Can somebody think of a formula that works so that we can easily figure out, say, what the 100th term is without figuring out all the 99 before it? What is the 100th term of this? Can we figure it out?
-1.
-1. What's the 97th term? I heard a positive and a negative.
Or it's positive 1.
Yeah, 97 is positive 1. So the terms are either 1 or -1. 1 if n is it odd? The odd terms are all 1. The even terms are all -1. Or we could write x sub n, I suppose, is -1, maybe to the n plus 1. An odd plus 1 will give us an even, -1 to an even will be 1. An even plus 1 will be odd, -1 to an odd will stay -1. So we can put this as a more explicit formula, a recursive formula. Actually, in terms of what we're thinking, this is probably the most straightforward one to do it. To think about it, to realize none of these terms are getting close to a specific number, because a bunch of them are really close to 1. They are all 1. The other half are all really close to -1. There's not one specific number that they're all getting close to. Well, that leads us kind of to the other idea we want to look at today, besides the unbounded idea. And there's more I want to talk about in unbounded, but that may wait until Friday. But this idea where we've got kind of terms jumping all over the place. From a sequence. A subsequence, A sub n sub k, of a sequence, A sub n, is like the way the book defines it, and I'm not sure I like my way of defining it any better. Is taken from A sub n without changing order. So maybe we'll take the first term, the 7th term, the 23rd term, the 24th term, the 64th term. What we can't do is come back to, oh, now let's pick up the 32nd term. That would change the order. So that's what I mean without changing order. So something like A sub 1, A sub 6, A sub 12, A sub 13, A sub 107 or 101, A sub 108. We decide to just take some of the terms, but we never circle back. So once you pick a term, the next one you pick has got to be farther down the list. The book does some terminology about a strictly increasing sequence of positive integers, but this works as a subsequence. A sub 1, A sub 6, A sub 3 does not. Because we went back. So we're not just picking elements out of the sequence in a random order, we're picking them out so that whatever one we picked out, the next one is farther down the line. And the next one's farther down the line still, and farther down the line still. And there's an infinite number of subsequences of any sequence. Now, what we want to kind of think about is, what's the relationship between a limit of a subsequence and a limit of the sequence? Is there a relationship between the two? And what does that relationship tell us? So, let's think a little bit about that. So, if we've got a sequence that is headed to some number, and we've got a subsequence can we know anything about A sub n? A sub n sub k? Can we conclude anything about whether it converges or not? And if we decide it converges, do we in any way know where it's converging to? And if we're not sure whether it converges, can we give any sort of argument about why we're not sure it converges? So we've got a big sequence that's headed to a limit, and we're just kind of randomly picking out a subsequence and trying to decide, do we know anything about that subsequence? There's only two options. It converges.
Have to converge to the same thing.
Okay. So
That's my vote.
that's your vote. That it has to converge to the same thing. So Jordan's theorem here would be that this converges to L also. All right.
Does our definition of a sequence entail that it keeps going indefinitely, or can it stop at some point?
It keeps going indefinitely. Yeah,
Okay, then it will meet the same limit eventually.
yeah. And the subsequence as well keeps going as well. Yeah, the whole idea of the sequence, it's an infinite list. And we're selecting some of the infinite list, but we're not changing the order. And so we've got another vote for that it converges to exactly the same limit. Regardless of what the subsequence is. And that's sort of an interesting thing to think about, because we're not sure how we're picking the subsequence. So how might we argue that? Or kind of what thought process were you going through to think that was the case? Because that is the case. So I think you were on the right track. So what was sort of leading you to that conclusion?
If the sequence reaches a limit that eventually, say, every figure in that sequence is going to be within a certain epsilon. If you are picking the odd number out of that sequence, if you keep going far enough, then you will only be able to pick things within that epsilon.
Yeah, I mean, if all the terms are within epsilon, and your subsequence, you only pick some of the terms, well, past this same spot, whatever terms you end up picking, well, they've still got to be in there. Now, we don't know what terms we're picking, but we have to keep picking, and at some point we have to be picking past this point where they are all less than epsilon. So it can't be going anywhere else. It has to be going somewhere. It has to be going to exactly the same limit. What if so let's think about, suppose I try to reverse this. We get what's called the first subsequence rule. I'll write it over here. That says A sub n is divergent if it has two subsequences that converge to different limits.
How would that be the case? So if we just said that they,
It's too.
oh, because it's backwards.
Yeah, it's backward. I mean, it is flipping things. Because if the sequence is convergent, then all the subsequences have to go to exactly the same limit. So if somehow we've got a sequence that has two subsequences that are going to different limits, well, there's no way that the entire sequence could be going to anything. They can't all be getting close to one specific value if two smaller pieces of them are going to two different values. Now, we don't know which pieces we picked, but if they're going to two different values, taking all the terms, they can't be going to just one value.
But if they're subsequences, how would they go to different values? If we just said that if it's a subsequence and the normal sequence goes to something.
Well, okay, if the normal sequence is converging. So we kind of flip things here. We've got this sequence, we're trying to decide if it converges or not. We don't know. But we identify, oh, this sequence is headed to 1.
Okay.
This subsequence is headed to 1. This subsequence headed to -1. That's enough to say, oh, our sequence diverges. And we don't have to go through, well, it can't go to this, it can't go to this, it can't go to this. It's a much easier process than we had currently of pick a limit, no, it can't go to that limit. Pick a different limit, no, it can't go to that limit. Let's come up with our argument, it can't go to any limit. If we can find two subsequences that do go to limits, because we're a lot more adept at proving it is converging to something. So the example we had looked at, the -1, +1, -1, +1, -1, +1, fits this very well. Take all the -1s, they're headed to -1. Take all the positive ones, they're headed to +1. Two subsequences converging to different limits. The original sequence is diverging, and we don't have to dive in and try to argue based on the definition that the sequence is diverging. We can argue based on the subsequence rule, that it's diverging because I could identify two specific subsequences that are converging to different limits. Okay. I think that's a good place to stop because I've just got like 4 minutes. I do need to come back and talk more on Friday about this idea of the limit of A sub n being infinity. What do we mean by something being unbounded? How do we work with that? Are there some other things we can do with that? Because there is a sense we've kind of seen and dealt with that idea a little bit before when we were talking null sequences. 1 over a really big number. So we kind of have this sense of what things get really big, but what's our standard of proof on what do we mean it's getting really big? Beyond our sort of intuitive, I think really big is what we need here. So that's where we'll pick it up on Friday. And I'll again try to bring the camera for you. Well, for you, because today's for Becca, who said, I'm not feeling well. Like, I can come if you want. It's like, well, not especially if you're not feeling well.
Sorry.
Yes, that's why I told you before, because if I wait until after, I'll not remember at all. So, I got a call from a mom at Fairplay, ninth grade daughter, been getting A's all the time and is now failing math and crying every night. And